So we'll start with the revision first. So in the previous class we had seen how to find the temperature of the earth with no atmosphere. So let me very quickly go through the stuff which we did in the previous class. So the concept is this energy balance. Now Somil, this is a revision for you as well. So I had given a value of power which the sun emits from its surface. So do you recall that value? What is the energy emitted from the sun, from the sun's surface?
It is, I don't remember what is emitted, but I remember like the solar constant, like
Okay,
what is received by the atmosphere.
okay, so let me just tell you the power which sun emits, that value is 3.95 into 10 to the power 26 watts. So you can go through your notes, we had actually calculated this. Now using this we had found out what is the energy which Earth's atmosphere receives using the inverse square law. Let's say this is the height at which the sun's atmosphere is. So we had seen this intensity value is 1.4 kilowatts per meter square. This is what we call the solar constant, right? Now the concept behind this particular topic is we have to find the temperature of the earth. So what we have done, what we had done was, let us say initially there was no temperature, the earth was at 0 kelvins assuming, and then the sun starts to emit its radiations and the energy comes in the form of circles. So let me, so using this particular example, so if I consider sun as a big torch, we had seen that the sun's energy is incident on the earth in the form of circles, and then it actually hits the earth's surface, right? So now there are two cases. First we have to find the temperature of the earth with no atmosphere, and then we'll do the with atmosphere thing. In the previous class we had already done this, the temperature of the earth with no atmosphere. So let me very quickly walk us through the concept. So if the intensity of energy at the atmosphere is 1.4, assuming that there is no atmosphere, then even at the surface, let's say this is the, if I consider this as the surface, so this intensity will also be 1.4, assuming there is no atmosphere. Now using all of this we have to find out what is the temperature of the earth. So the concept is, when the sun's energy is incident on the earth in the form of circles, so let me draw this. So these are the dotted lines, and the sun's energy is incident like this, and this circle moves to the right, correct? Now because of this incident energy, the temperature of the earth starts to increase, and using the Stephen Boltzmann law, we know that whenever any object has any temperature, it radiates energy across its entire surface area. So basically what is happening is, there is incoming energy and there is outgoing energy from the earth. Now at a steady state these two values are equal. So let's say if EA represents the energy which is absorbed by the earth, and ER, let's say, is the energy which is radiated from the earth. At the steady state we had seen that the value of EA and ER basically balance each other out. At this particular condition we have to find out what is the temperature of the earth. So let's go step by step. So the energy which is absorbed by the earth, that is, for that we use the solar constant, which is 1.4 kilowatts per meter square. So first we will figure out what is the total energy which is incident on the earth. So that will be the intensity, which is 1.4 kilowatt per meter square, and then we multiply that with the area of this particular circle, let's say A naught. So that will be pi r square, where r here stands for the radius of the earth, and this value you have to remember as 6400 kilometers, right? And intensity value is 1.4 kilowatts per meter square. Now if we solve for this particular expression, if you put all the values, this particular energy, by the way, this is actually not energy, this is in all, everything of this is in terms of powers, these are powers. right? Because intensity, if we multiply that by area, we will get power only, because the formula for intensity is this: intensity is power divided by the area, correct? Now if I just put all of the values, what value I'm going to get is this: incident energy will be 1.8 multiplied by 10 to the power 17 watts. So this is the incident energy which is coming in from the sun. Let's say if I represent that as EI, this is the incident energy. Now the concept is, assuming that there is no atmosphere and we are considering the earth as a perfectly black body, so we assume that the E value, emissivity value for earth is 1 in this particular case. So what the condition is, the energy which is absorbed by the earth, that is equal to the energy which is incident on the earth, because E is equal to 1, and that's why we say that the energy which is absorbed by the earth, that is equal to 1.8 into 10 to the power 17 watts, right? So this is the left hand side of the equation. Now we will find out what is the radiated energy. Now for that we will use the Stefan's Boltzmann law, and that law states that the power is AE sigma T to the power 4. So as I said, the emissivity value we assume as 1. Now for A we will consider the total surface area of the earth, which will be 4 pi r square, because earth is considered a sphere, and the value of sigma we can put, and this entire expression. So if I put all of these values, the radiated energy will come out like this. So 2.9 multiplied by 10 to the power 7 multiplied by T to the power 4. So this is the right hand side of our equation. So if I equate this with the left hand side, and if we solve for this, eventually we get the value of temperature as 280 kelvins, and this is 7 degrees Celsius. So this was the entire working. How do we find the temperature when there is a condition that there is no atmosphere, and second, the earth is a perfectly black body, because of which we say that the value of emissivity, that is equal to 1. Using these two assumptions, eventually we arrive at this expression for temperature, right? So this was the temperature of the earth when there is no atmosphere. Now the next topic starts when we have the atmosphere. That is like the first topic for this class. Now Sheldon, did you understand the entire working behind all this?
Yes, a little bit I did. But can I write this down real quick so I can revise later?
Okay, you write it down.
Yes, sir.
Okay, Spera, so this is the same concept which we did in the last class, so just revise
Yes, sir.
through it.
I was there in like in starting.
Okay, but just revise through this, because the next topic will involve this working. If you have already revised, then just figure out a way how do we find the temperature of the earth if we consider there is an atmosphere.
So if there is an atmosphere, then like the values for emissivity and albedo will change.
Perfect, yes, that is the
Because
goal.
other than that, all the other values like the surface area and the sigma, those values remain constant. So these two are the only things
Okay,
that can
so let
change.
me give you the values and see if you can figure out the answer. So the value of albedo A you can take as 0.3 for the earth, and the value of E can be taken as 0.6. See if you can figure out the temperature.
So this is including the atmosphere.
Yes, this is the next topic. If you have the atmosphere, the value of A will be 0.3 and the value of E is 0.6. So the entire calculations remain the same. The only difference is we have to incorporate these two factors, A and E.
So like the LHS of 1.8 into 10 power 17, does it remain the same?
No, it will change, because see, if we again, so this is like a classic hypothetical case with no atmosphere, we assume that whatever energy is incident on the earth, that gets absorbed by the earth. That is one of the assumptions which we are using. But in this particular case, there is an atmosphere, and we consider the real earth where A is 0.3, which means, let's say if 100 joules is coming in from the sun and reaching the earth, 30% of it is reflected and 70% of it is absorbed by the earth.
Oh, okay. So we have to multiply the intensity with 1 minus albedo.
Yes. So see if you can get the answer, let me know. And Sheldon, let me know when you finish writing.
Yes, I'm done writing.
Okay, you're done writing?
Yes, I'm done writing.
Okay, so anyway, Sheldon, even if you have any problem still understanding this, you can let me know later. All right, so we'll go through the concept again. Okay, so now we come to the next topic, when we find the temperature of the earth when there is an atmosphere. Okay, so see, in this particular case, the calculations will remain, the approach will remain the same, and the approach is the energy which is coming in, from the sun, let's say that is the E incident energy. In this case, this will not be equal to the energy which is absorbed by the earth, and whatever the energy which is absorbed by the earth, we have to equate that to the energy which is radiated. This is the whole concept. Now let me show you a diagram. So here you can see you have sun's energy which is coming in, and there is an atmosphere, it goes through the atmosphere and then it reflects from the surface, right? So now one part of the, let's say E is the total energy which is coming in. Now one part of this energy will directly get reflected away from the clouds. Let's say this is E1. Now the rest of the energy, that is E minus E1, that will go into the earth, and some part of it is getting reflected and one part will get absorbed into the earth. Now whatever energy is going out, that is also reflected back. This is what we call the greenhouse effect. About this we will consider the working later on, but the whole point is whatever energy is coming in from the earth, that is not equal to the energy which is absorbed by the earth. That is where the factor of albedo comes into the picture. So the value of A for earth can be considered as 0.3. So this is the average value of albedo for the earth's surface, that is 0.3. Now in the previous case, let me show you. Okay, so if you can see, the energy which is incident we found out as 1.8 into 10 to the power 17 watts. So let me just write this down. Okay, so the incident energy is 1.8 multiplied by 10 to the power 17 watts. Now the value of A is 0.3. This means that 30% of the energy is getting reflected, and the rest of the energy, which is 70%, that will be get absorbed into the earth, which means if I take 70% of the incident energy, we will get the energy which is absorbed by the surface. So that will be 0.7 multiplied by 1.8 into 10 to the power 17 watts. So this will be the left hand side, that is the energy absorbed. Now we will find out what is the energy radiated. Now in this particular case also, the right hand side will change. The formula remains the same, that is A E sigma T to the power 4. Area of cross section remains the same as earlier, sigma is a constant, but the value of E will be different. In the previous case, we had assumed that earth is a perfectly black body, which means we took E as 1, but in the real sense, the average value of E for the earth is 0.6. So the expression which we have found out using A sigma in T to the power 4, that was 2.9 multiplied by 10 to the power 7 T to the power 4. So all we need to do is just multiply 0.6 into this. So that will be our right hand side. So now do one thing. So equate these two values and then tell me what is the value of temperature. So all of you just try to do this.
Yes, sir.
I'm getting it as 18.3.
Okay, let me check. So what is that value in Kelvin?
291.
Yes, yeah, that is correct.
So this albedo and E that we have taken, this is also considering the greenhouse effect, right?
Yes, yes, yes. So even greenhouse effect is also of two types. One, we have the natural greenhouse effect, and then we have the forced greenhouse effect, which is because of the pollution on the earth. This is a whole topic we'll cover later on. So Sheldon, Smera, just tell me what are the temperature values, what you get. Vaibhav, you just joined in.
No, sir, I joined in like 5 minutes ago. I was looking at these.
Okay, so were you able to understand anything from this slide?
Yeah, it's the Boltzmann thing, right, for
Yes,
radiation, and
yes.
you're just equating the both. Yeah,
The only difference
I'm just
is,
writing.
did you go through the previous classes notes by any chance?
Yeah, I went through last class's notes.
So in the previous case, there are actually two cases when there is no atmosphere, and this is the second case when you consider the atmosphere. So when there is no atmosphere, we consider the hypothetical conditions that the value of A and E for Earth is 1. Now the only difference in this is, if I take A as 0.3, that means
Yeah.
30% of the energy gets reflected and only 70% of it is absorbed. So 70% of the incident energy, that will be your left hand side, and in case of your radiated energy, we put E as 0.6 in place of 1, and we find the temperature.
Okay. Wait. Yeah, makes sense.
So just equate these two parameters and tell me what is the value of temperature in kelvins. Smera, did you solve it?
So I'm not doing it.
Okay.
So 18 degrees Celsius is correct, right?
Yes, 18. You are getting 18.3, right?
Yeah, 18.3.
That is approximately correct. Anyways, let me just cross check again.
So I'm getting my answer to be 291.71 Kelvin.
Yes, that is correct. So convert that to degrees Celsius now.
Okay, sir.
Yeah, so 18.7 in Kelvin.
Yes, sir.
Okay,
18.71 Kelvin.
just a second. All right, so I'm getting 291.7 in Kelvin, and if I subtract 273 from it, we'll get 18.7 degrees Celsius. So Saumil, just check, it is 18.7, not 18.3.
Yes, so I'm getting my value to be 18.56. Yeah, I don't know what's going on.
See, okay, just let me.
So I'm getting it as 0.3 only, not 0.7.
Okay, so let me check.
So what I actually did was I didn't take 1.8 into 10 power 17.
Okay, then
Like
what did you
what
take?
I did was I wrote the entire formula out, and anyways the pi and the
Okay,
radius
okay,
square gets cancelled. So that's why I got. So
okay.
that's why that rounding off factor went away in my answer.
All right. Anyways, that is fine. Even if you're getting 18.3, that is fine. These are close enough. So approximately that is the right answer. Anyways, the actual value is not important. What I wanted you to note was the approach, because that is what you will use in the questions. Is that fine? Okay. So now let's move on. So is everyone done writing? Can we move on to the next?
Yes,
Yes, sir.
All right. So now we come to the last topic of this particular chapter. There are other topics as well, but those are more theoretical in nature. So let's consider nuclear power first. Now there are two concepts in this nuclear power. One, we have the fission and the fusion reaction. Now can anyone tell me what is the basic essence in a fission reaction? What happens in a fission reaction?
So like you bombard the nuclei with slow electrons, and that triggers a reaction. Like the
Yes.
big nucleus splits into two small nuclei, and it releases a lot of energy.
Correct. So let me give you a basic explanation. Let's say A is a nucleus of a particular atom, and it has protons and neutrons. Now there are certain nucleus where the number of neutrons exceeds, it is not the neutrons, there is a specific neutron by proton ratio in every atom. So there is something called a optimum value of neutron by proton ratio that decides the stability of a nucleus. In some particular nucleus, there are too many neutrons as compared to the protons. So those nucleus are called the radioactive nucleus, because they are unstable, and in their natural state they want to transform into stable atoms, stable nucleus. So consider A is your unstable radioactive nucleus. Now to convert this into the stable forms, let's say B and C are the stable forms after splitting. So to help this out, we add some sort of elements, catalysts, to aid this transformation. So for that, let me just give you a basic definition of fusion fission reaction. So nuclear fission is a nuclear reaction in which the nucleus of a large atom, which is unstable, and that splits into two or more smaller lighter nuclei. Now there is something called a fusion reaction, that is the exact opposite of it, in which there are two atoms which are getting connected to form the bigger atom. That will be fusion. So this is nuclear fission, right? Okay. Now just have a look on the diagram on the left. So we have a uranium nucleus, that is uranium 235. Now 235 stands for the mass number. Mass number means the number of neutrons plus protons. So the number of neutrons plus protons in this uranium is 235. Now this is a radioactive nucleus, which means it is highly unstable. Now on fission, there are two products which form. One is called the krypton, and then we have the barium. Now to help this entire fission process, we take a neutron and we hit that into the uranium nucleus. So uranium nucleus, so this neutron, which is a subatomic particle, this enters the uranium nucleus, and see, when you have neutron plus proton initially as 235, if you add one more neutron, that will become 236. So this is that 236 what it represents. Now the uranium 236 is even more unstable as compared to uranium 235, and it automatically splits into two stable nucleus. So one is krypton and we have barium. Krypton's mass number is 92 and 142 is for barium. Now just consider the number of just consider the mass number. So you have a 236 here and you have a 92 and a 142 here. So do one thing, if I add 92 and 142, what do we get? Just tell me the value.
34.
So 92 plus 142 will give you 234, which means there is a difference of 2, because there was 236 the overall mass number, there is 2 left. Now to account for that, the 2 more neutrons are released, because there is 1 neutron here and another neutron here. So 234 plus the 2 neutrons, that becomes 236. So this is just to check whether the equation which we have made, that is correct or wrong. So if I write down this entire process in a nuclear reaction, so this is that nuclear reaction. So we have a uranium whose mass number is 235 and this is atomic number. So let me just give you an example. Let's say if M is any particular nucleus, you have A and Z. Now the number below which is called the subscript, that is called the atomic number, and A, which is the superscript, that is called the mass number, right? So all we need to check is if the bottom number, so you have a 92 and 0, and this should be equal to the right hand side. So 36 plus 56 also gives you 92, which means that is correct. Same thing we can do for the upper number. So 235 plus 1 gives you 236, and then if we see there are 2 neutrons, and if you add 92 and 142, that will give us 236. So this is the way to write down this nuclear reaction. And since this is a fission reaction and initially you had an extremely unstable nucleus, on release it will generate a huge amount of energy. So we can write that in the equation itself. Now after this there is something called a chain reaction. What do we mean by that? So when one neutron hits one uranium nucleus, it produces 2 neutrons. Now since the sample which you have, it will have millions of nucleus of uranium, so consider any one more uranium nucleus. So the neutron which is produced will hit this uranium nucleus, and it will again go through the same reaction, and it will keep on generating more neutrons, and those neutrons will keep on hitting the uranium nucleus, which are still unreacted. So the whole thing can be shown like this. So originally we have the uranium 235, the neutron hits this, it becomes the uranium 236, which is even more unstable, and that decomposes into 2 fragments, krypton and barium, and there is a huge amount of energy. Along with, there are 2 more neutrons are produced. Now these 2 resulting neutrons hit more uranium nucleus which are there in the sample. So this entire process keeps on repeating itself, and that is what we call the chain reaction. And in each chemical nuclear reaction, the energy is extremely high, and there are millions of such reactions happening throughout the sample, which means the total energy for the entire sample is extremely huge, and that is so huge that it is very unsafe to use that. So there are various ways to control that energy. So we will see that later on, how do we do that. But as of now, please write down what is there in this particular slide. and let me know when you finish writing.
So should we draw all the diagrams as well?
Yes, if you want, because anyways I'll send you the presentation. So
Okay,
you can make a block diagram, later you can make the whole thing.
Yes, sir. Done.
Okay, great.
Done, sir.
All right, Smira, what about you?
Yes, sir.
That's all.
Okay, great. Now let us proceed. So this was just the basic mechanics of a nuclear fission reaction. Okay, now this is the same reaction which we did. Now for this particular slide, what we are going to do is we will find out what is the amount of energy that is released in one fission reaction. So how to do that? For that we have to understand the basic mechanics of the mass number and atomic number. So AXZ, this is the nomenclature to represent any particular nucleus, where X is the nucleus or the atom. So this is the atomic symbol, so which means U is the atomic symbol for uranium, and the number on top is called the mass number, which is 235 in case of uranium, and the below number, the subscript, is called the atomic number, which is 92 for the uranium. Now atomic number means the number of protons in the atom, and mass number means the number of protons and neutrons. So do one thing, if we have a uranium nucleus, tell me how many protons are there and how many neutrons are there.
For 92 protons and 235 and 143 neutrons.
Yes, correct. So 143 neutrons and we have 92 protons. So this is the so you can find the number of protons and neutrons in each case. Now the first step to find the energy is to just check if your reaction is correct or not. So for that we consider the numbers on the bottom. So you have a 92 and a 0. So 92 plus 0 will give you 92. Now we check the right hand side. So 2 multiplied by 0 is 0. Then you have a 36 and then you have a 56. So if we add 0, 36 and 56, we will get a 92, which means the number of protons balance each other out, which means this is correct. Now we will check for the mass number. So you have a 235 and a 1, which will give you 236. Now we see 2 into 1 will give you 2. Then you have a 92 and a 142. So if we add 2, 92 and 142, we will again get 236. So this is a way to cross check whether your reaction is correct or not. So the mass numbers should equate as well as the atomic numbers, right? So this equation is correct. Now we check what is the, how do we find this out? How do we find the energy? So the basic principle is the any nuclear reaction or any chemical reaction for that matter, it follows the law of conservation of mass as well as energy. Which means if I consider the left hand side, the mass of the left hand side has to be equal to the mass on the right hand side. So let's check if that is the case. So if you consider this particular table, you have the different atoms, uranium, barium, krypton and the neutron, and the masses of these atoms are given to you in terms of U. Now U here stands for AMU, and this is called the atomic mass unit. So do one thing, just to check if this reaction is following the conservation of mass. So just take the left hand side. On the left hand side you have the uranium, one uranium and one neutron. So add the masses of uranium and neutron and tell me what is the mass, total mass.
So it comes out to be 237.054227.
Okay, just let me check. The others also please cross check. Okay, so Samuel, what was the value which you were getting? 237 point?
0.054227.
Okay, correct. So this is the left hand side. Now if I consider the right hand side, check what is the value of the masses on the right hand side, where you have 2 neutrons, 1 krypton and 1 barium.
Here it is 235.859959.
Okay, others please tell me, are you getting the same values, Smera and Vaibhav?
No, sir, I'm not getting that. 1 second.
Just cross check.
Sir, I'm getting 327
On the right hand
points.
side?
Yeah.
Okay, let me check. So you have 1 krypton which is 91. Then you have
Oh, sorry. I did 2 atoms for krypton. My bad.
oh no, there is 1 krypton, 1 barium and 2 neutrons.
Yeah, 235.8.
Okay, and Smera, are you getting these two values?
Yes, I'm getting 235.859.
So the same values, right, which I have written here.
Yeah.
Okay, so now you can see here that the value on the left hand side, that is greater than the value of the right hand side. Now it appears that this particular equation is violating the law of conservation of mass, but it is actually not. So what basically is happening is the difference of the mass gets converted into the energy. So there is something called the mass defect, which is delta M. Mass defect for a particular reaction, that is equal to the mass on the left hand side minus the mass on the right hand side. So tell me, what is this mass defect value?
1.194268.
1.19
194268.
268. Okay, Smera and Vaibhav, just tell me, is this the correct one? Just cross check.
Yes, sir.
Alright, so this is the mass defect. So basically what happening is, this mass defect is responsible for your energy. Now why this happens? This is actually a concept from the relativity principle, which we'll consider later on. As of now, you just have to remember that the difference of mass gets converted into the energy. So how do we find that? How do you convert the mass, which is, okay, by the way, the unit for this is AMU, atomic mass unit. So let me write down this whole thing again, just a second. So delta M, that was 1.194 268 AMU. Now just write down one conversion factor. So 1 AMU that is equal to 1.66 into 10 to the power minus 27 kgs. So convert the mass effect into kgs and tell me what is the value.
Uh, 1.982 into 10 power minus 27.
Okay, just a second. So 1.982
times 10 to the power minus 27.
Okay, so this is in kgs, right? So the principle is, if you have any mass defect, so we need to multiply the mass defect. Okay, just a second, let me check the values. Okay, so please write down one more conversion factor. So that is 1 AMU, that is also equal to 931.5 mega electronic volts. Okay, so now convert this AMU into the MeV and tell me what is the total mass effect.
So what MEV is a unit of energy and AMU is mass. So
Kg,
how can we?
yes, correct. So this is not actually equal, but this is like corresponding to, because 1 AMU mass can generate this much energy. So this is not exactly equal, this is like analogous. 1 AMU is analogous to 931.5 mega electronic volts.
I'm getting 1.846 times 10 to the power minus 24.
Okay. Saumil and Smela, you also tell me your values in mega electronic volts.
So is it somewhere around 780?
Okay, let me check, just a second.
Oh wait, it has to be more than 931.
Mm-hmm.
It is 1112.
1112. Weber, was this your
That's what
answer?
Oh, um, so wouldn't you multiply it by the mass in kg or?
So see, the AMU can be converted into kg. That is, you have to remember. But for this particular case, we want to convert the mass into energy. So we just multiply the mass
Oh,
effect
the okay, yeah, then 1112. That makes sense.
MEV, right? So if I want to convert this into joules, do you know how to do this? How to convert MEV into joules?
I think you multiplied with 1.6 into 10 power minus 13 or something.
Yes, because M stands for 10 to the power 6 and EV electronic volts is 1.6 into 10 to the power minus 19 joules. So multiply all of this and tell me what is the final energy released in joules.
1.78 into 10 power minus 10 joules.
10 to the power minus 10.
Yeah.
Okay. Vaibhav and Smela, you just cross check.
Yes, sir. 1.78 times 10 to the power minus.
Minus 10 joules, right?
Yes,
Alright,
sir.
so this is how we find the energy. So the concept is you have to find the mass on the left hand side and the mass on the right hand side. For a fission reaction, the mass on the left hand side is greater than the mass on the right hand side, and the difference of the mass gets converted into energy, and the conversion factor is this. So the 1 AMU is able to generate 931.5 mega electron volts amount of energy, right? So this is the energy which we were supposed to find. Now, so if we consider 112 MeV, this is a high energy. So okay, just a second. All right. Okay, so if you consider any sort of fission reaction, the energy produced is pretty high. So for that, what we have to do is, all right, so basically what is happening is there is a uranium 235 nucleus. It is being attacked by a neutron atom. Now, because of the high amount of energy which this particular reaction generates, let's say on fission we have the krypton and barium and another 2 neutrons. Now these 2 neutrons again attack a uranium present in the sample. Now because of this extremely high energy, these neutrons are moving with extremely high kinetic energy. Now it is very much possible that the neutrons are moving so fast that it just passes through the nucleus without any reaction taking place. So for the reaction to take place, the neutron has to get absorbed by the uranium nucleus. Only then the radioactive decay occurs. So for that we do something called a moderation. So by moderation of neutrons, we mean that the neutrons need to be slowed down so that the uranium is able to absorb the neutron. Otherwise, if it is moving very fast, it will pass through the nucleus without any radioactive decay. So the definition is this. So the chain reaction can only occur if the neutrons are moving slowly, otherwise they will pass straight through the nucleus. All right, so okay, this is right. So to make a chain reaction, these neutrons need to be slowed down, and this is done by introducing some nuclei in between the uranium nucleus. So how do we do that? So this is the process. So you have a uranium 235, it was hit or attacked by a neutron atom, then it splits into barium and krypton, and a huge amount of energy is released that is in the form of kinetic energy of the neutrons. Now if this particular neutron passes through the uranium nucleus at a very high speed, then there will be no reaction if the speed is very high. So in the sample we introduce moderator nucleus like this, which are primarily there to slow down the speed of the neutrons before and when they hit the uranium. This particular velocity is optimum enough for the nuclear fission reaction to take place. So please write down the whole of this down.
I hadn't written down the entire derivation of what we did in the previous two slides.
Okay, so you actually should have stopped me. So should I let me go back? This one?
Yeah, from here.
Okay, so write it down.
I am done with this one.
Okay. So please write down all of this.
Just to confirm from the previous slide, all we needed to know that like one fission reaction it releases around 112.5 MeV.
Yes.
So where did the value of 172.8 come
Yes,
from?
so there seems to be some error. I'm just checking that. In the meantime, just write down everything else. I'm just checking that there seems to be an error in the calculations. Just a second.
So I think there was an error in the mass defect.
Okay, so just let me go back. Where do you think is the error?
Sorry.
So where do you
Like,
think
I
is
think
the
the
error?
calculated value of mass defected is coming to like 1.2. I think it should be lesser than that because when we did this rule, we got some lower value.
Oh, yes, yes, good. But according to the calculations, let me check. Okay, so let's do one thing. I'll check this. In the meantime, are you done with the writing that moderation part?
No, sir, not really.
Okay, so please do one thing. Write down this moderation, and in the meantime, I'm cross-checking. Oh, got it. So, okay, so I got the mistake. Before that, just let me know when you finish writing this moderation part. Smera and Vaibhav, let me know when you are done writing. So Saumil, this value 172.8 mega electron volts is correct. So write this down, and then we'll go back to check how we are not getting this.
Yes, sir. Done.
Okay, Smera, what about you?
Yes, sir.
All right. Sheldon, have you written it down?
Yes, I'm updating.
Somil, you are done writing, right?
Yes, sir.
Okay, now let's check this value. This 172.8 mega electron volts is indeed correct. So good thing it was there. So let us go back to the calculations. Yes, I'll tell you where the mistake is. So see, this particular nuclear reaction is although correct, but the value in the table, if you see uranium, the mass which is given to you is not of uranium 235, but it is for uranium 236, right? So this is the mistake
Yeah.
which we have done. So basically what is happening is the uranium 236 is getting converted into krypton, barium and 2 neutrons. So the right hand side will remain the same, but the left hand side will change. So M1 is not this value, it is just this much. The left hand side will be 236.045563 AMU. This is the M1. Now check and tell me what is the new mass defect.
0.185. Yeah, this is the value that we had got in
Yes,
school.
0.185. It should be 604
0.1856.
AMU. So everyone, Vaibhav and Smera, please correct this. This is the correct mass defect. Vaibhav and Smera, did you understand what the mistake we were doing?
Yes.
So basically in the question, sometimes they will give you the value of uranium 235. In that case, you have to add the neutron as well. So we need to make sure what kind of mass have they given for 236 or 235. So since this is the new mass defect, if we go to the next slide, so this is 0.185604 AMU. This conversion is correct. So all we need to do is multiply the mass defect with 931.5 mega electronic volts to find the energy released. So now tell me what is the energy released. So basically we are multiplying.
It is 172.9 MeV.
Okay, 172.9 MeV.
Right.
So this is found out by multiplying the mass defect with 931.5 mega electronic volts. So we will get 172.9 mega electronic volts. Now if I multiply, if I want to convert this into joules using this conversion factor, so tell me what is the final energy in terms of joules.
For 2.77 into 10 power minus 11.
Perfect. This is indeed correct. So the whole concept is, this is the correct value. 172.9 is the energy released in during the one nuclear fission reaction of uranium. So the whole point, so this is a very good thing. So in the questions, in the exams, we have to just check whether the mass given is for uranium 236 or 235, because sometimes they do give the mass of 235. All right. So Smera and Vaibhav, have you collected the calculations?
Yes, sir.
Yes, sir.
Okay, great. So this is what was written on the next slide. So the when the nucleus splits, it releases about 172.8 MeVs, and this is a very high energy. That is why we needed the moderation, right? So this was the whole concept behind the nuclear fission. Now let's do a few questions based on this principle. Yes, so please go through this question and tell me your answers. Did anyone get the answer?
No, sir, I'm confused.
Second.
Somil, you're done?
Yes, sir.
Tell me your value for part A.
For A, I got 1.93 into 10 power 16 joules per kilogram.
Okay, can you tell me your approach?
So like what I did was the energy value they have given, it's for one uranium 235 nucleus, right?
Yes,
So,
correct.
oh wait, I think I made an error over here.
Okay,
I took the
cross-check.
mass to be 1 U for, by mistake, so I think I should have taken it as 235 U.
Yes, that will be 235U.
So the corrected value I'm getting it as 8.2 into 10 power 13.
Yes, good. That is correct. Okay, just a second before you proceed to part B. Vaibhav, Smira, did you get part A?
No, sir, I'm not getting this answer.
Okay, just let me explain. So first, the specific energy is equal to the energy released. We will divide that by the mass in kgs. So it is given that you have one uranium 235 and it releases 3.2 into 10 to the power minus 11 joules of energy. So this will be your numerator, and all we need to do is to find the mass. For that we do not need the density. So since it is a uranium 235 nucleus, which means the mass of this will be 235 U, where U is the atomic mass unit. Now in the previous slide I had showed you the conversion factor, that 1 AMU is equal to 1.66 multiplied by 10 to the power minus 27 kgs. So to convert U into kg, we use this conversion factor to find the total mass. So the mass in this case will be 3.9 multiplied by 10 to the power minus 25 kgs. So this will be your denominator. So now just solve for this and check what is your answer, and see if you are getting this value 8.2 into 10 to the power 13, and the units will be joules per kg. So Smira, Weber and Sheldon, just check this out.
Yes, sir. 8.2 into 10 raised to 5.
Good. Weber, you getting this answer? Sheldon, also check.
Yes, sir.
Great.
Makes sense.
All right. Sheldon, did you understand this?
Oh, yes, sir.
Okay. Now, Samuel, what was your answer to part B?
Uh, 1.56 into 10 power 18.
Yes, that is also correct. So could you explain how did you do that?
Yes, sir. What I did was like I used the formula. The density is equal to the energy density upon the specific energy. So since we had the density and specific energy, we can find the energy density.
Good. So either we do that, or let's go start from the basics. So energy density formula is this: the energy, we divide the energy with the volume of the nucleus. So which means energy you already have it, so the volume is what you need. So density is equal to mass divided by volume. So the volume can be written as mass divided by density, right? So the mass you had found out as 3.9 into 10 to the power minus 25. If we divide that by the given density, which is 1.9 into 10 to the power 4, you will get the volume. So on solving this, you should get something like 2.052 into 10 to the power minus 29, and the unit will be meters cube. So this will be your new denominator. So in place of volume you place this value, and on eventually solving you will get so Saumil, what was the value? 1.54.
Yeah, I got 1.56.
Okay, so 1.56 into 10 to the power 18, and the units will be joules per meter cube. So this is the answer. So please write this down, all of you.
Yes, sir, I got the same answer. 1.559 into
Nice.
10 to the power 18.
Yes, sir.
Good.
Same, sir.
And Sheldon, did you understand?
Yes, I got it. I was writing it down.
Okay, good. So write it down and let me know when you finish. So we do the next question then.
Got it, sir. Now writing.
Okay, great. Now just we'll do one more question. So this one is a little tricky question, so please read the question carefully.
So,
Yes.
so is it like
I got
3.33 into 10 to the power 6?
Not really, but anyways, tell me your approach.
Wait, I
I also
think
got the
I
same answer,
got the
sir.
mistake. I'm
Smera?
getting it now as something like 1.43 into 10 power 6.
Just cross check and tell me your approach, because the value is not that high. Smera, are you getting the same answer as Somer?
Yeah, I got 3.33 into 10 raised to 6.
Could you tell me your approach? How are you getting that answer?
So, like, I first converted 1 megavolt into mega electron volt into electron volt.
Okay,
Then after that, I subtracted 0.1.
all right.
And it was really simple. And then I divided it by 0.3,
Divide that by 0
which is like 30% of the kinetic energy.
Okay, so the answer what you're getting is still energy. You are dividing energy by a percentage, so the answer is still energy, isn't it?
Yeah.
That is not giving you a number of collisions. Are you getting it? So what you had done was you had taken 1 mega electronic
Yeah.
volts and subtracted the 0.1. This numerator
Yeah, I
is
got my mistake.
okay. So anyways, let me explain how to solve this. Vaibhav, by any chance, did you solve this?
No, sir, I didn't get this either.
Okay, so let's read the question. So that's why I had told you to read it carefully. There is a catch. So when a moving neutron strikes a stationary carbon 12 atom, the neutron loses about 30% of its kinetic energy. Let's say you have a C12 and you have an incoming neutron whose energy is 1 MeV. So after a collision, 30% of the kinetic energy is lost, which means the remaining kinetic energy is 70%. So if I take 70% of the 1 MeV, that is the kinetic energy of the neutron after one collision, right? Now let's say it hits another C12 atom, and what do you think is the kinetic energy after the second collision? Can you figure this out? So it starts with a 1 MeV.
7 square into 1 MeV.
Could you repeat?
0.7 into 0.7 into 1.
Perfect. So 0.7 into 0.7 into 1, that will be the kinetic energy after the second collision. Similarly, following the same pattern, the remaining kinetic energy after the third collision can be directly written like this: 0.7 to the power 3, and that will be in mega electronic volts. So let's say if I consider n as the collisions, number of collisions which you need to find, so the kinetic energy of the neutron after n collisions will be 0.7 to the power of n mega electronic volts, and this should be equal to the value which is given to you, which is 0.1 electronic volts. So now solve this equation and tell me what will be the value of n. Smera, Vaibhav, Sheldon, did you understand how have we written this 0.7 to the
So,
power?
but RHS is an is an EV and left hand side is an MEV.
That's fine. So the EV can get cancelled out. So all you are left is an M. See, M
So that will be
basically
10 to the power 6.
M basically can be replaced with this factor 10 to the power 6.
So would it be inside the bracket or outside the bracket?
It will be outside the bracket. Smera, Vaibhav, Sheldon, did you understand? How did we get 0.7 to the power of n?
Yes, sir.
Okay. So solve and tell me the value of n.
It's 45 collisions, right, sir? 45.1.
So 45 point.
One, yeah, 19.
All right. So since the value of n has to be an integer, so we will take 46 as the answer.
Yeah.
Not 45. So others, please check if you're getting 46
I
as the
get
answer.
this value. I'm not getting anything even close.
Okay.
Like, first of all, I'm getting a negative answer, so it's not even possible.
Okay, let me solve it. So you have a 0.7 to the power of n. If we multiply that with 10 to the power 6, that will be equal to 0.1, right? So the 0.7 to the power n can be written as 10 to the power of -7, right? Because this 10 to the power 6, it goes here on the right hand side. Now we can you can use the calculator, or directly if I use the log, if I take log on both sides, n log of 0.7, that will be equal to log of 10 to the power minus 7. Now the base of log is 10, which we take, so on the right hand side you will just get minus 7, and on the left hand side you will get n times log of 0.7 to the base 10. After this you can use your calculators and check what do you get.
I got 45.2. Like previously what I had done was I did not simplify that 0.1 divided by 10 power 6 and I directly put it in the brackets. That's why I think I was getting a different answer.
So you're getting 45.2, right?
Yeah,
And
45.2.
since n has to be an integer, so we take 46 as the answer to this. All right, Sheldon, did you understand the principle behind this?
Yes, sir. Let me just write this down.
Okay, please write this down. Smera, any doubts?
No, sir.
Sheldon, let me know when you finish.
Yeah, sir, I'm done.
Okay, now one more question before we wrap up this topic. This is appears difficult, but it is quite easy. Just go through all the parts. Let's go step by step. First, solve part A and B and let me know. Give me a moment.
So I'm done with A and B.
Okay, tell me, what is your answer to A? Somil, what's your answer to A?
For A, I'm getting 7 neutrons.
Yeah, same sir.
Great, yes. Smera, are you getting 7?
Yes, sir.
Good. Sheldon, did you get it or should I solve it?
Actually, ask the thing, so
Okay, so let's see how to solve this. So you have a plutonium nucleus whose mass number is 239 and atomic number is 56, which is given to you, this one. Now it is given a plutonium splits into two atoms, zirconium whose mass number is 96 and xenon whose mass number is 136. Now the atomic numbers of xenon and xenon are given to you. So Zr is 40 and xenon is
So, but 40 plus 54, it does not give us 56, right? So there's some error, I think.
yes, there is an error. So how did you get 7 then?
So
Sir,
because
I
for
got
number
it
of
from,
electrons, it's only the mass number which is required, not the proton number.
yeah, the mass number.
Oh yes, correct. So
And mass numbers seem to be correct.
let me check what is the just, uh, in the meantime, go to the next parts. Let me check the atomic number. It's actually 94, not 56. So there is a typo in this question. Atomic number of for plutonium is 94. So Sheldon, make this correction.
Yes,
Now
sir.
you can see since we are supposed to find the number of neutrons, before that earlier I had explained, so you have a number on top gives you the mass number, which is protons plus neutrons, and the number on the bottom gives you the number of protons. Since we need number of neutrons, which means the only number which you require is the number on top. So if I see 239 on top, so on the right hand side you have a 239, and if I, oh sorry, the left hand side, the right hand side, see if I add 96 and 136, Sheldon, tell me the value.
Yes, sir.
So the right hand side mass number we have to find out. So the mass number of Zr is 96 and 136 for xenon. So if you add these two, what will be the value?
Oh, okay, one second, sir. You gave us 232.
232, right? So which means the left hand side is greater than the right hand side. So how
Yes.
to account for this anomaly? So we add the neutrons. So let's say if I add neutrons, so for neutrons the number on top is written as 1. So if I consider, let's say, x as the number of neutrons which is released, so the right hand side's mass number will be 232 plus x into 1, and then you have to equate this equation. So 239 on the right hand side is equal to 232 plus x. So the value of x which you are going to get is 7. Now Sheldon, tell me, is it understandable or should I explain again?
Yes, sir. No, no, now. Okay.
Alright, so this will cover both of your first two parts. Now check the next parts.
So for the
Mhm.
for C, is it 2.62 into 10 to the power minus 11
What is the unit?
joules?
Okay, do one thing just to cross check, find the value in MeV.
MEV,
So
I'm getting 164.
Yes, that is correct.
yeah,
Good.
164.
Yes,
Oh,
164 is the right answer for C.
So and I think the D part is 239 grams.
What is the mass of 1 mole? 239. Yes, that is correct.
So for E part, is it 2.52 into 10 power 24?
Yes, good. That is correct.
And F part, I'm getting it as 686.2.
Okay, how much F part was how much energy is released in EV? So what's your answer?
686.2.
You need to check that. That is not correct.
Sorry, I got my mistake. The answer is too small. And it's wrong.
So for F, if you consider 1 kg of plutonium, how do you calculate the mass defect?
Okay, just let us check. So did
So
you get
it's
the all the
for
parts before that,
find
Vaibhav?
Yeah, I've done everything else.
Okay, just a second. Somil, yes, what you are saying?
for F part I'm getting 4.13 into 10 power 26 MeV.
MeV, yes, that is correct. So, Vaibhav, this is the right answer, 4.13 to 10 to the power 26. Take a few minutes, think over it, and then I'll explain.
Okay.
So they had actually asked the F part in EV, but I gave it an MEV. So like, is there a mistake?
That's fine, that's fine. MEV is fine.
And G part is just the conversion. So I'm getting 6.6 into 10 power 13 joules.
Yes, good. That is the right answer. Okay, now Sheldon, if I start with you, did you solve C part?
So I'm still doing this.
Should I explain C?
Yeah, sure. Yeah, sure. So it will
See,
take
for
me
this
some time anyway.
C part, so the principle is you have to find out the mass defect delta M, which is the mass on the left hand side minus the mass on the right hand side. So if we see our reaction, on the left hand side you have the plutonium atom, and if you see the table, the mass for plutonium is given to be this 239.052158 U. This is the mass. So the left hand side mass, let's say this is A, let me give you the names A, B, C, D. So the left hand side is A, and on the right hand side you have 1 zirconium, 1 xenon, and 7 neutrons on the right hand side. So which means if I take 1 zirconium's mass, which is B, and then the mass of xenon is C, and then there are 7 neutrons, so we will multiply the D with 7. So if I do this calculation, you will get the mass defect. Did you understand this, Sheldon?
Yeah, sir.
So now solve for this. Tell me, what is this expression? Vaibhav, did you get the concept of F?
No, so I'm still confused.
Okay, so basically what is happening is the answer which you found in C, that was the energy released when one plutonium splits into the zirconium and xenon, right? So all you have to do is just check what are the total number of atoms in 1 kgs of plutonium.
Oh, so you just multiply it by
Yes, correct.
164. Okay.
Yes.
Okay, yeah, 4.14 into 10 to the power 27.
Yes, so and then convert that into joules as well.
There is 6.6 and 6.62 into 10 to the power 14 joules.
Yes, that is correct. 10 to the power 14. That is should be 10 to the power
I got
13. Just
30.
check.
13. Okay.
Sheldon, what is this value? Delta M?
I'm getting it as 0.25. But since it's mass defect, we should just take it as kilograms.
No, no, it is not 0.25.
Yeah, I'm getting it.
Just okay. Smera, could you tell me your value of delta M?
So I got 0.176.
Yes. So Sheldon, please cross check. The delta M is 0.176. and a
082.
Okay, then, sir.
So there might be a
So I
calculation
got
error.
082.
0.17.
6082.
Okay, 082. All right.
So I got 602.
You
I think I must have made a mistake.
so it should be 6022. Anyways, that won't make much of a difference. So see, Sheldon, this is the mass defect in AMU. Now the concept which you use is 1 AMU releases 931.5 mega electronic volts of energy. So all we need to do is just multiply this mass defect with 931.5 and you will get the total energy released. And if you do the multiplication, your answer will be approximately 164 MeV. So Sharon, please write this down.
Yes, sir. Done.
Okay, now let's move on to the next part. So D says, what is the mass of 1 mole of plutonium? Samuel, could you explain how did you solve this mass of 1 mole?
So the relative atomic like the mass of 1 mole, it is the same as the mass number of any
Okay,
atom.
yes. So Sheldon, the concept is if you have any atom X, A, Z, so 1 mole of X will weigh a grams. So in this case, we have to find the mass of 1 mole. Now the mass number for plutonium is given to you as 239. So the mass of 1 mole will be 239 grams. Right, so that is D part. And E is how many atoms are there in 1 kgs of plutonium? Smera, can you tell me how did you solve E part? Smera,
Yes, sir.
how did you solve E part?
So, sir, like, I had like some trouble here, but like I thought like after like finding a mass of 1 mole of plutonium, you can use like the see.
See, the way to do this, 1 mole of any atom has Avogadro's number of atoms, Na, whose value is 6.023 into 10 to the power 23. So 1 mole which weighs 239 grams has this much atoms. So we need to find out when the weight is 1 kg, what will be the number of atoms. So to do that, we take the Na, we divide that by the 239 and multiply that by 1 kgs, which is 1000 grams. So put Na as this value and solve for this. You will get 2.5 into 10 to the power 24 atoms. Sheldon, did you understand this?
Yes, sir.
Smera, is it clear?
Yes, sir.
How did you have solve it in the first place?
So like I used like in the mass of 1 mole, I had done like use the mass like of the what do you, like U mass. So using that, I tried to do it.
Were you getting the same answer?
No, sir, it was different.
No, that which means the approach is incorrect. So write this one.
Yeah.
Now for the F part, it is easy since you have found out the total number of atoms, and in part C we had found out what is the energy released when 1 plutonium splits. So what was that value? That value was
164.
164 mega electronic volts. That is the energy released when 1 plutonium atom splits. So we multiply that with the number of atoms, which is 2.5 into 10 to the power 24. So if we solve for this, we will get 4.13 multiplied by 10 to the power 26 mega electronic volts. So that is the answer to part F. Sheldon, did you understand this?
Yes, sir. I do like this.
And for the part G, we have to convert the answer into joules, so that is easy. The M is 10 to the power 6 and EV is 1.6 into 10 to the power minus 19 joules. So if you solve for this, the answer to part G, let me write it here. So the answer to part G is approximately 6.6 into 10 to the power 13 joules. So please write down all of this, Sheldon, and later on you have to go through this question again.
Yes, sir. Yeah, that's related.
Alright, Smera, did you write the F part?
Yes, sir.
Alright, so now we are left with just one topic, that is the last topic for today's class, and that is this activity. So before I explain, just write down this definition.
Yeah, done, sir.
Great. So so if I consider uranium 235, so uranium 235 is a radioactive nucleus, which means this is unstable and it wants to split. So if uranium atom splits, we saw that it splits into two components, krypton, barium and neutrons. So this is true for any radioactive material, it will split into stable components, stable atoms. So this is what we say, this is one radioactive decay reaction, or the number of disintegrations. So let's say if you have a sample of uranium, it will have millions of uranium atoms, so it will disintegrate, each atom will disintegrate according to the reaction. Now the concept is how many disintegrations are taking place, what is that rate. So the rate of disintegrations, how many uranium atoms are disintegrating per second, that is what we call the activity of that particular element. This is also equal to the number of unstable atomic nuclei that decay per second. So for example, let's say if you have 1000, for example, if you have 1000 atoms of uranium at T is equal to 0, and let's say at that point the activity is A0. So after some time, let's say after 10 minutes, the number of atoms which are still left, which are undecayed still left, which are, let's say that is 900 atoms. So which means within 10 minutes 100 atoms have disintegrated. So after 10 minutes 900 atoms of uranium 235 are still left, and this was the activity at T is equal to 0. The concept is the activity of any radioactive material that is directly proportional to the number of nuclei present of that element. For instance, at T is equal to 0 there were 1000 atoms, so the activity was directly proportional to 1000. At T is equal to 10, since the number of nuclei has fallen, which means the activity will also fall. So the rate of decay, that is actually falling with time. So assuming, let's say A0, let's say if I take any random value A0 by 3, so the activity value will keep on reducing as the number of atoms are reducing, right? So a naught by 3. So now there is a concept called half-life. Now Saumil, are you aware of this? What do we mean by half-life?
Yes, sir.
What is it?
It is the amount of time taken for half of the nuclei in the sample to decay.
Okay, perfect. So let me write this down. So time for half of the material to decay. So which means, assuming initially we had 1000 atoms, after some time t, let's say that is t time, after that time we are left with 500 atoms. So which means the 1000 is being divided into 2, so 500 atoms are left. So the time taken when this happens, when half of the atoms have decayed, this is called the half-life, and that can be represented like this in the questions, t half. So that is our half-life. So please write all of this down, then we'll proceed. Let me know when you finish.
Done, sir.
Great. Okay, so a few more additions. So see, at t is equal to 0 there were 1000 atoms and the activity was A0. And what does activity represent? The number of disintegrations per second. So which means the uranium was disintegrating at a much faster rate initially at t is equal to 0. So I have told you this activity is directly proportional to the number of nuclei present. So if the atoms were 1000 and the activity is A0, if the atoms are halved, so 1000 becomes 500, then the activity will become half. So at t is equal to t half, the activity comes out to be A0 by 2. So if I want to draw a graph in which on the y-axis we have the number of nuclei present and on the x-axis we have time. So the graph is an exponential graph like this. So you can see that initially, so at the lower times when the time is just started, the rate of decay is much faster, and as you keep on increasing the time, the rate also falls. So this is a rough diagram in which we represent the
What
activity.
is
Sorry,
on the graph? What is meant by n?
n is the number of nuclei present. So initially we have, for example, in this question we had 1000 atoms. So the on the y-axis this will be 1000. After 10 minutes, let's say this is 900, and at half-life, so if I consider this as t half, so at this time the number of atoms will be 500. So draw this diagram. Can we proceed?
Yes, sir.
Vaibhav, Smera, are you done?
Yes, sir.
All right.
Yes.
So let me draw the same diagram. So this is like that representation. So the same thing on the right hand side, you can see there are the number of nucleus present, and on the x-axis we have the time, which incidentally has been taken in multiples of the half-life. So initially there were 1000 nuclei. So after one half-life that drops to 500. So 1000 divided by 2. In another half, so this is first half-life. In the second half-life, from t half to 2 times t half, the value drops from 500 to half of it, which is 250. Now as you can see, in the first half-life, during the first half-life, the number of nucleus were reducing at a much faster rate as compared to the second half-life. This is an indication that the rate of disintegration is decreasing. Similarly, if we consider the third half-life, so after third half-life, the number of atoms will drop from 250 to half of it, which is 125, and this process carries on. Right. So just draw this diagram, and then we are left with just one more slide. Let me know when you finish. And rate is nothing but the activity, so that is reducing.
Done, sir.
Okay, great. All right, so just one more important concept. So if you observe the table, initially we had this much nuclei in the picture, and which keeps on reducing. Now the whole concept is this keeps on reducing until it will reach a value which is extremely close to 0. Now can anyone tell me at what time will the value of n become 0? After how many half-lives is n 0? Just think over it. Somil, any idea?
I'm thinking so. 1 minute.
So there is no need to actually calculate. The answer to this is actually we cannot determine that time. The answer is CBD, cannot be determined. Why is that? Because although the value of n is decreasing, but if we observe any exponential graph, so in the exponential graph, this particular line, it never touches the x-axis. It will go extremely close to the x-axis, but it will never reach the
Yeah,
x-axis.
y is equal to 0 is like the asymptote for the
Yes, that is an asymptote. That is why even if you consider millions of years, even then the value of n will not be 0. It will be very close to 0, but it is never 0. Right, so this is the concept. Okay, now before we wrap up today's class, there is one last question which I want you to do, and then we finish. So read this question and solve it.
So 30,000 years.
Yes, great, good. So how did you do it? Smera, could you explain the solution? The answer is correct.
Oh, sorry, sir. I just realized I'm on mute.
Okay.
So, I divided 200 counts, by 2 raised to x. So, I
Okay.
tried different values of x.
That's fine. All right. So, Vaibhav, Somil, Sheldon, did you solve it?
Yes, sir. What I
Yes,
did
sir.
was 200 into 1 by 2 raised to x is equal to 10. So, like, whatever value I got, I just rounded it
So
up to the
even that
nearest.
is
So
fine. Let me,
same.
Vaibhav, I was saying something. Vaibhav, did you get the answer?
Yes, sir. I use the same approach as Swami.
Great.
Yes.
Sheldon.
Also, I'm redoing it because I think I got something wrong.
Okay, let me explain. See, carbon 14 has a half-life of 6,000 years that is given to you. Initial activity is 200. So we have to find how long will it take for this activity rate to fall below 10 counts. Let me give you a very basic approach. So let's say if we start off with T, let me draw a table only. So T half and activity, and you have the time. So initially, let's say if I take time t as 0, so the activity in this case is 200 counts per minute. So if I consider one half-life, so one half-life, just a second, okay, 6,000 years is given to you. So which means this is 6,000 years. And I already told you after one half-life, the activity reduces by half. So 200 becomes 100. If I take another half-life, which means 12,000 years, so then 100 will drop to 100 divided by 2, which is 50. If I consider another half-life 3, so that will give me 18k, and the activity will become half of this, which will 25. So now we have to check when does the activity fall below 10. So if I divide 25 divided by 2, that will give me 12.5. If I divide this further by 2, we will get 6.25. Right, so now just check. So 12.5 happens at the fourth half-life when the value is 24k, the time is 24,000 years, and at the fifth half-life the time is 30,000 years, and that's when we see that the activity has actually fallen below 10 counts per minute. But for this particular chapter, this answer is enough, but this is not the exact answer. But because if you see, between the 4th and the 5th half-life, the activity will cross over the 10, right? So the answer is not exactly 30,000, it will be somewhere between 24,000 and 30,000. But for this particular chapter, this much is enough. So 32,000 years is the right answer. Sheldon, did you understand this?
Yes, I now got it.
Okay, great. So so this is the end of today's class, but you have a small homework, which is this. See, initially when we started this chapter, I had told you that this particular chapter has a lot of theory. So all of these chapters are theory, which are very important. You will get questions in your exam, so please read through these topics from your book. That will be your homework. And that ends now. Okay, before we